So hello everyone. So today I'm gonna talk about our quest to write beautiful domain logic. Let me introduce myself. My name is Pierre, aka GhostDog PR online. I'm a French who lives in Seoul, South Korea. I created the Caliban library that I presented in Scala Matsuri 2 years ago, and I also contribute to some libraries in the ZIO ecosystem. I'm a developer at a Korean gaming company called DEVSISTERS, and we launched a social RPG game called COOKIERUN Kingdom in January of last year. This game exists in Japanese, so maybe you've heard about it. So the game became pretty popular with over 40 million downloads and pretty high load at any given time. And all of these game servers are entirely written in Scala using a purely functional programming style. Okay, so today I'm gonna first briefly introduce our architecture, and then I'm gonna discuss about what's special about our domain logic, and then go through several implementation choices and finish with some example. Okay, so there are two important concepts to understand about our architecture. I don't have time to explain them in details, but I just mentioned them briefly. So the first one is CQRS, Command Query Responsibility Segregation. So I have some diagrams to explain it. So basically, when we receive a request from the client, if it's a command, so command is something that modifies something like add, update, and so on. We forward this command to something we call an entity. So an entity can be like a user or a guild, for example. And a given entity exists in only one place in our cluster at any given time. So for example, all the commands for a given user will go to the same entity, and the entity will process these commands one by one. That's the part that we call domain logic. It's processing the commands. And then we use event sourcing. So instead of traditional CRUD application where we add or modify the data directly, with event sourcing, we just write events. We save events for everything that's happening inside our entity. And we persist those events in an event store. We also send them to Kafka. And then we have stream processors that consume this data from Kafka and create projections. Projections are an easy way to access the data. So we use those projections when we get queries from the client. When it's a read-only query, we just quickly access it from projection. So basically, this is how our architecture looks like. And today I'm going to focus in the orange circle about the domain logic. How did we implement that part? But it's important to know the whole picture, because what I'm going to talk about is quite specific to this CQRS / event sourcing architecture. Okay, so what is domain logic in our case? We have two main kinds of business logic. First, we have transitions. So transitions is the action of taking a state plus an event and then getting a new state. For example, we have a user state, we have an event like a reward received with some coin, and then we have a new state where the coin amount will be increased according to the event. And then we have what we call programs. So programs is you have a state, you receive a command, so the client wants to do something, and then you get a new state with a list of events that have been triggered, and maybe also a result. So those are the two main pieces of domain logic that we have. And I'm mostly going to focus on programs here because transitions are kind of included in programs. So what are the other requirements that we have when we write business logic? So we might return a result. Sometimes the client needs a response to a command, we might fail. So when the client asks something, we check that all the parameters are correct. And if it's not, we return a validation error, and then we don't do anything. And we might require access to some environment or configuration. In our case, we have a lot of game rules, and there are many constants and many things that game designers can configure. So we need access to that to implement our domain logic. Another very, very important constraint is that there should be no side effects when we run that domain logic. Why? First, because it should be replayable. When we load an entity, because we don't store the full state in a database, we just load a snapshot and then we replay events one by one until we get to the current state. So when we replay those events, we don't want a side effect to happen again. Otherwise, it's going to happen every time we load an entity. Also, if there is a validation error, we don't want any, we don't want to do anything. We just want to fail without any effect. So if there is a side effect that happens before the error, it's a problem. So we don't want, that's another reason we don't want any side effects. We also have the concept of transactions across entities. So between two different users or a user and a guild. So if the command succeeds in one side but fails on the other side, we want the transaction to fail, and we also don't want any side effect in that case. If we want side effects, we run them after the events have been persisted. So not in this part of the code. And finally, our domain logic needs to be fast. In our game, the domain logic is pretty complex because every time the player does something, we need to validate hundreds of quest requirements, if a quest has been completed, a mission, if you unlocked some item, and so on. So altogether, the domain logic part takes over 50% of the CPU of our game servers. So this is quite important in our case. So how do we write this in Scala? So a transition would be like a function from an event and a state to either an error or a new state. And a program could be seen as a function from an environment and a state to either an error or a new state, a list of events, and a result. So when we implement our domain logic, what we want to do is just write simple for comprehension with those primitive operations of succeed, fail, get the state, get the environment, or lifting an event. So how to implement that? How to implement the program of A, for example. So one option is just to use plain function. So that's the most naive approach. So you say a program is just a function from environment, state, and maybe previous events to an error and new state, new events, and a result. And then we could use the monad instance that is defined in libraries such as CATS, SCALA-Z, or ZIO-PRELUDE, and then just use this flat map and write for comprehension with those functions. However, using plain function is not very convenient. This data type is not made for that, so it's not very ergonomic. Another problem is that flat map is not stack safe. And another problem is at every operation, you need to unlift this function, this either and this tuple, and recreate it every time. I will show an example of that after. So a better approach would be to use a data type that is dedicated for this purpose. So in the CATS library, there is a data type called index reader writer state T that is really designed for this case. It takes a type parameter F. In our case, we would use either because either allows failure, eval doesn't, or IO as well. So this data type is pretty convenient. However, when you look at the implementation, you can see that the implementation is actually similar to what we had before. It's a function. So whenever you flat map, you need to, again, unlift all those components and recreate them. So when you flat map, you have to use shift and then map, map, and combine. So there are a lot of operations at every flat map. So if you have a lot of it, the performance will not be optimal. So another option would be to use ZIO. So ZIO has 3 type parameters, R, E, and A. So in the R type parameter, the environment, you could stick your environment, your state, and also your events and modify them directly. And then in ZIO E and A type parameters, you could return an error or fail with a success. The performance will be quite better because you don't need to unlift and lift at every flat map, because when you flat map, it's just creating a case class called flat map. And then it's the ZIO runtime, the interpreter, that will handle it later. So performance will be better. However, there is one problem with using ZIO for that. With ZIO, ZIO is too powerful, basically. With ZIO, you can run any effect. And as I said, we don't want side effects in this part of the code. Our team knows that they should not run any side effect outside of ZIO. But if the type is ZIO, the temptation to run side effect is pretty high. And there is a high chance that during code review, we might miss that someone ran a side effect because the type was written in ZIO. So one option that is interesting is using CATS MTL. So basically, CATS MTL is a bunch of interfaces that expose some functionality, and then you can use you could use ZIO in the background as your F, but because you don't use ZIO directly, because you use those interfaces, you only have access to what those interfaces are exposing. So you only have access to failing with an error, getting access to the state, or lifting an event. So this is quite interesting. It has a similar performance, but hiding the full power of the monad that you are using underneath. However, it's also not so great, especially for ergonomics. The type inference, when you use generic F, is not ideal compared to just using a simple data type. And everything relies on implicit. So it requires a little boilerplate, like functions are less discoverable. If you miss the proper imports, you might not find what you need. And also monad error is invariant with the E type parameter. So it's not so convenient to eliminate or change the error type compared to ZIO, compared to using ZIO directly. So one solution that we finally moved to is using ZPURE, which is a type in the ZIO-PRELUDE library. So it's similar to CATS index reader writer state T in the principle, but the implementation is closer to ZIO. It's a single data type. And when you flat map, there is no unnecessary unlifting and lifting. There is an interpreter that will handle it when you run it. And unlike ZIO, ZPURE doesn't let you run any side effect. You can only do succeed, fail, access to the state, lift event, access to the environment. That's all it does. So it's really designed for our use case. To confirm the intuition about the lifting and unlifting issue that I mentioned before, we ran some benchmark. The benchmark are just reading the environment, lifting an event, and modifying the state in a loop a lot of times. And as expected, the ZPURE solution is much faster than the solution where you have to lift or unlift some events. It's also faster than ZIO because it's much more lightweight than ZIO, because yeah, ZIO can do a lot more things than what we need here. So how does it work in practice? We don't use these data types directly. Instead, we made a custom DSL with the basic operations, and then we build our functions using this DSL, and we assemble our functions like Legos. So an example of our DSL is we have this pure function that succeeds. We have this raise error that fails with an error. We have assert that to check a condition and fail. Extract option. We have also get, inquire to get the state or the environment. Lift event. We don't have a set state because you never modify the state directly. You can only lift event, and the transition from this event will change the state. Then based on this DSL, we can build more complex functions. So for example, here you see we use type aliases such as guild program to not have those very long signatures everywhere. And then we have functions. So for example, inquire guild metadata returns a guild program of guild metadata. Inquire requester ID. So we just combine those primitives from our DSL. And at the end of the day, this is how our domain logic looks like. We have a function here, join guild, that returns a guild program of unit. And then when you read this, you see we get the guild metadata, we get the requester ID, we get the guild state and check how many members there are. And then we assert that the count of member is not is lower than the max. Otherwise, we fail with a validation error. And if there is no failure, we continue and we lift an event, guild member joined. Then the transition for this event will add the member to the guild state. So why is this beautiful? When you look at this code, you notice that there is absolutely zero noise. It's not polluted with technical consideration. It's 100% focus on our domain logic, which means that it's easy to read, it's easy to maintain, and if there are new developers coming to our team, they are able to read this and start writing this kind of code easily, as long as they understand the domain they are working on. Also, using this way, our code is independent from the program implementation. So actually, we started with using CAT's index reader writer state T, and then we moved to MTL, and then we moved to ZPURE. But without changing much of the logic. We just changed the DSL implementation, but the rest of the code was not changed much. So it's easy to switch from one to another. And finally, it is fast, and fast makes it beautiful as well. All right, so that's it for this presentation. I invite you to try our game. As I say, it exists in Japanese. We are also recruiting at DevSisters. Scala developers. And yeah, before I finish, I just want to say that what I showed today is quite specific to our use case and our load. So for example, if you don't have so much load on the domain logic part, the performance might not be as important as it is for ours. So I think all of the options are pretty good option in some cases, like based on your load, the other options might be also good for you. So I hope this was interesting. And maybe if I have a little time, I will check the questions. Let me go back. さん、ありがとうございます。トラックチャットの方では結構盛り上がっているみたいなんですけれども、今は質問は、今入力中の方がいますね。Yeah, maybe I will answer the questions in the chat directly after, because I will need some time to read it. はい。わかりました。それではピエールさん、どうもありがとうございました。それではまたチャットや、はい、雑談の方で次はお願いいたします。